Okay. How many glucose molecules? So we say, how many glucose molecules? C6H12O6 molecules can you make with? And our initial quantity is 4.8 times 10 to the 5 O atoms. Okay, so that's what we're starting with. And then we need to convert from O atoms. So we need the O atoms to go on the top or the bottom. They need to go on the bottom, O atoms. And we need to find the C6H12O6 molecules. So we will put that on the top, C6H12O6 molecules. And what is the ratio between C6H12O6 and O atoms? So you always take the large particle, yeah, and you say, I have one of those. If I have one of those, how many O atoms do I have? I have 6 of them, okay? So this is what we call, do you remember? It's called the particle ratio. It's the particle ratio, and you simply do it by looking at the formula and counting the atoms, okay? Okay, and what, 48 divided by 6 is 8, so we get 0.8 times 10 to the negative 5, which would become 8.0 times 10 to the negative 6. Not negative. Why am I saying negative? That should be positive 5. And if I made that bigger, then that should be a 4. So that would be times 10 to the 4 O atoms. Is good? Okay. Now we need to find chromium 3 hydroxide. So chromium 3 hydroxide, we have Cr3+, we have OH-. So our formula for that is CrOH3. And how many of those can we make from 342 times 3.42 times 10 to the 10 hydroxide ions? So how many CrOH3 can we make from 3.42 times 10 to the 10? And the formula for hydroxide is OH- ions. So we have our unknown, that is equal to our initial quantity times the conversion factor. And so we write times, and then we draw a line. And we need to cancel. What are we canceling here? OH- ions. And we are finding CrOH3. And again, this is a particle ratio. How do we find the particle ratio? You look at the formula, okay? Look at the formula, and then you simply count. What are we counting in this case? So we look at the big formula, this one, and what are we counting? We are counting the OH minus ions. How many do we have? 3. So we have 3 OH ions for every 1 CrOH3. So if you're getting confused by how to write those, the formula of the compound, there's always going to be one of those, like the big compound, and then there will be many of whatever one of the subunits is. It could be oxygen atoms, it could be chromium atoms, it could be hydroxide ions, whatever. Okay? And we get 42 divided by 6 is 7, so divided by 3 is 1.14 times 10 to the 10 CrOH3. So we have 1/3 of the number of particles of CrOH3 as we do hydroxide ions. Yeah? Okay. How did you guys find the 2 videos? How many people did not watch the videos yet? Okay, that's all right. Only one of you? Okay, good. I'm glad you all watched the videos. Yes? You watched the video. Okay, sorry. I'm confused. It's all good. So you guys should be able to tell me that 1 mole of particles is equal to 6.02 times 10 to the 23. And I want to point something out to you. Do you remember how your periodic table was as easy as 1, 2, 3? If you have trouble remembering this here, this exponent, it's as easy as 1. Whoops, see, I'm erasing rather than writing. It's as easy as 1, 2, 3. Isn't that nice? So if you're like, was it 22? Was it 24? What was it? It's 10 to the 23. 1, 2, 3, essentially. Okay? So you can use that as a conversion factor. Now, what I never want to see, should I ever see 6.02 times 10 to the 23 moles? That's a lot of moles. That is a mole of moles. Yes? So that's like saying, sometimes people will do this. They'll be like, is equal to 6.02, like 1 molecule. And I want you to do some thinking before you ever write the numbers down. Does it make sense that 1 molecule is equal to hexillions and hexillions and hexillions of molecules? It just doesn't make sense. So when you're writing your conversion factors, make sure you're turning your brain on so that you're looking at it and going, have I written the numbers where it makes sense? And if you have trouble figuring that out, just remember you should never see a mole of moles, never 6.02 times 10 to the 23 moles. That will end you in hot water. It'll be bad, okay? All right. So today we are going to Actually, we are going to start exploring molar mass a little bit because we need to do that in order to be able to work with our hydrate lab. So I think that is this one. No. 5.2a is on page 34. Page 34.
When you write, your tone influences how real.
In this video, we're going to look at how we can use moles to count the number of atoms we have in something. So, for example, here I've got a container with a bunch of chunks of carbon in it. I want to know, how many carbon atoms do I have here? We'll learn how to figure that out here. So, just a quick review of moles. A mole is kind of like a dozen, except there are 12 things in a dozen, and there are 602 hexillion things in a mole, and we often abbreviate this number in scientific notation as 6.02 times 10 to the 23rd.
Okay, so I'll give you a second to copy that down. Did I make you write the big long number? No. Okay, good. I figured I did it a while for the first time, but it's good to know that it is a huge number, and if you have to write all those zeros a few times, you will remember that it is a huge, huge number.
Now let's take a look at a mole. Right here, I have a mole of sulfur atoms, which is just about 602 hexillion sulfur atoms.
So that just drives home the point. That is 602 hexillion sulfur atoms. How big are atoms? Like so small your brain cannot even imagine how small they are. To have 602 hexillion of them in this tiny, tiny little dish, right?
Now, this is pretty crazy because it's such a giant number of sulfur atoms. Here's my question. How do I know that there are 602 hexillion sulfur atoms here, right? I couldn't count them out for two reasons. One, atoms are way too tiny, right? We can't even see them with a very powerful microscope. So there's no way that I could have seen the atoms and counted them out.
One.
Second of all, even if I could count out the sulfur atoms, there are so many things in a mole that it would take 20 quadrillion years to count from 0 up to a mole. So even if I could see these atoms, there's no way I could count them out. Yet I'm pretty confident that there are pretty close to 602 hexillion sulfur atoms in here. How do I know that? Well, we're going to learn more about this, but it turns out that I can figure out how much a mole, 602 hexillion sulfur atoms, weigh, and then I can put this thing on a scale and weigh out that number of sulfur atoms. Let's talk a little bit more about this so it makes a little bit more sense. Okay, so here's an analogy. Let's say that I work at a candy factory, and when someone places an order, it's my job to count out all the pieces of candy that they ordered. Okay? One day, a giant rush job comes in for 10,000 jelly beans, and the person who placed this order wants exactly 10,000 jelly beans. What a pain this is going to be, right? I gotta 1, 2, 3, count out 10,000 jelly beans. It's like going to take all day.
Any guesses? Chat with your neighbors. See if you can figure out how you might do this more efficiently. Anyone have any clever ideas? Or not very clever ideas? Yeah? You could weigh them. How many would you weigh to start with, maybe?
100?
Sure, you could weigh out 100, because counting 100 wouldn't be that bad, right? And then if you wanted 10,000, you would need how many? 1,000, 100 of them? 100 hundreds. Yeah, so you would multiply that mass by 100 and you could just weigh out how many that is. And that is exactly what we do with moles. Okay? So we figure out how much does 1 mole weigh, and then we can just weigh out 1 mole at a time.
What could make my life a whole lot easier? Well, one thing that would be really awesome is if I knew how much 10,000 jelly beans weighs, right? So what if I figured out that 10,000 jelly beans weigh 27,130 grams? That would be really awesome, because then all I would have to do is put a big bag on a scale and just shovel the jelly beans in until I got 27,130 grams of them. So in other words, instead of having to count, if I know how much 10,000 jelly beans weigh, all I gotta do is weigh out that amount. We can do the exact same thing here with moles. I told you there's about 602 hexillion sulfur atoms here. Of course I didn't count that out. That's because I know that 602 hexillion sulfur atoms, a mole of sulfur atoms, weighs just about 32.07 grams. So
Now, I would like you to go take a look at your periodic table. And find sulfur. And tell me if there's anything you notice about sulfur on your periodic table compared with this sulfur, this mole of sulfur that he's talking about here. Yes.
The atomic mass is about the same.
The atomic mass is about the same. In fact, if we went to 2 decimal places on our periodic table, it would be 32.07. On our periodic table, we only go to 1 decimal place. So the atomic mass, measured in AMU, is 32.1 atom weighs 32.1 AMU. 1 mole of atoms weighs 32.1 grams. So an AMU is actually a fraction. It is a 6.02 times 10 to the 23. Yes, it is that fraction of a gram. And in fact, that's why we chose a mole, because it allows us to just scale up from atomic mass units to grams and have the number 32.1 be the same. If that made sense to you, that's fantastic. If it didn't, you can just go with it for now. Okay?
all I got to do is put this container on a scale, weigh out 32.07 grams, and I know I have just about 602 hexillion of them. So how did I know that a mole of sulfur atoms weighed 32.07 grams? Well, all you got to do is look at the periodic table. If I look sulfur up on the periodic table, I've got the element name and the abbreviation and stuff, and then I got this number down here. This is what we call the molar mass. And this number down here tells us how much 1 mole of this element weighs in grams.
So that number at the bottom of the periodic table, at the bottom of each square, it is the average atomic mass, but we also can refer to it as the molar mass. So sulfur, 1 sulfur atom weighs 32 point, I'm going to say 32.1 because that's what's on your periodic table, 32.1 AMU. 1 mole of sulfur atoms weighs 32.1 grams. And so we call that the molar mass. This is our atomic mass because it's the mass of one atom. This is the molar mass because it is the mass of one mole. Atomic mass, mass of one atom. Molar mass, mass of one mole.
So 32.07 is how much 1 mole, 602 hexillion sulfur atoms weighs. Now, let's go back to the candy factory. Imagine that I get all kind of orders for all sorts of different candies. I can figure out what 10,000 of many different types of candies weigh. So, for example, maybe I have to do M&Ms one day, and I can find out that 10,000 M&Ms weigh 8,770 grams. They weigh less because one M&M is much lighter than one jelly bean. So 10,000 of them are going to weigh less. On the other hand, a candy like one of these chocolate malted balls, very delicious, are a bunch heavier than the jelly beans. So 10,000 malted balls are going to weigh a bunch more, 154,600 grams. So it's the same way with atoms. Some are lighter and some are heavier. So carbon, for example, is a little bit lighter than sulfur. And 602 hexillion carbon atoms only weigh about 12.01 grams because carbon atoms are just lighter than sulfur atoms. On the other hand, something like zinc atoms are heavier than sulfur atoms. So 602 hexillion zinc atoms, a mole of zinc atoms, weighs 65.38 grams. And just as I did with sulfur, I know how much the carbon and zinc moles weigh because I can look up the atoms on the periodic table. So here we got carbon, 12.01 is its molar mass. That's how much 1 mole weighs. And zinc, look that up on the periodic table, 65.38, and that tells me how much 1 mole of zinc, 602 hexillion zinc atoms weigh. So, if I want 602 hexillion, 1 mole, of any kind of atom, all I gotta do is look on the periodic table and find out how much a mole of that atom weighs. And then I don't have to count any atoms. All I have to do is just weigh out this amount on a scale. This is just like me being lazy in the candy factory. I don't want to have to count out these jelly beans or M&Ms, so I can just weigh them instead. I can do all my counting by weighing. And that's what I do with these atoms. I count by weighing out their molar masses. So, now that we know how to figure out how much a mole of atoms weighs, let's go back to that original question that I asked at the beginning of the video. I have here in this container a whole bunch of carbon. I want to know how many atoms of carbon are in here. Let's see how we'll answer this. Okay, so how many atoms of carbon do I have in this container? Well, let's think about moles of carbon. I look up carbon on the periodic table and I find out that 1 mole weighs 12.01 grams. And I also know that in that 1 mole, there are 602 hexillion atoms. So the first thing I want to know is how many moles of carbon do I have here? In order to figure that out, we can do some weighing, all right? I know that 1 mole weighs 12.01 grams, so let's weigh this and figure out how many total moles we have in here. I put this on the scale and find out that there are 31.87 grams of carbon atoms in here.
Now, you know that we have 1 mole of carbon atoms has a mass of 12.01 grams. Could you find, using unit conversion, how many moles of carbon atoms are there in 31.87 grams of carbon? Do you think you can figure that out? I'll turn on the light so you can see a little bit better. You might need a piece of paper. I don't know if there's room there for you. Go help yourself to some paper. Okay, folks, on your scrap paper or whatever you've got, you want to answer the question here. So, and you know that 1 mole of carbon atoms equals 12.01 grams of carbon. Try to answer this using conversion factors. So you're going to write times and then a line. And you're going to put your units on the top, units on the bottom, see if you can figure it out. Anyone need some paper? Have some paper. Try the question. You got it? Yeah, try the question. What unit has to go on the bottom of this conversion factor here? Grams of carbon, yeah? And what unit has to go on the top? Moles. Now, we are told, and we can also start to just know this for ourselves, that 1 mole of carbon atoms is equal to 12.01 grams of carbon. And eventually, we're not going to tell you this anymore. We're going to say, look this up on the periodic table. So 1 mole of carbon atoms weighs 12.01 grams. Your grams cancel out. And you get, well, let's watch what Tyler does here. Okay. Because he'll give us the number and then I don't have to haul out a calculator.
Now that's more than a mole. If we had 12.01 grams of carbon, we'd have 1 mole, but we have more than that. So let's figure out how many total moles we have. We'll do that by taking 31.87 grams, the total mass of carbon atoms here, and divide that by 12.01 grams, which is how much 1 mole weighs. And when we do that, we get 2.654 moles. So that is how many moles of carbon I have in here. Okay, we'll take this number, hold on to it because it's going to be important for what we do next. Okay, so how many atoms of carbon do I have in here? Well,
do you think you could find out how many atoms of carbon there are? Give it a try. If you're like, I have no idea what to do you remember how to go between moles and atoms? 1 mole of atoms is how many atoms? 6.02 times 10 to the 23 atoms. Okay, so you're going to give that one a try. So you're going to take this number, 2.654 moles of carbon, and we want to find how many atoms of carbon. Yeah, we haven't finished the problem yet, so we're gonna, oh, yeah, and it would be 4. So we've got 4 and 4. But when we use 6.02 times 10 to the 23, that'll bring it down to 2. Yeah. So yeah. And remember, anytime you do a conversion, you need to write what sign goes here? Times. And then you need to draw a line. And then you say, what do I need to cancel? Moles of carbon. So moles of carbon go on the bottom. And then I'm trying to find atoms of carbon. And I know that 1 mole of atoms contains how many atoms? 6.02 times 10 to the 23 atoms.
we know that in each mole there are 602 hexillion atoms, but here I've got 2.654 moles. Okay, this isn't too hard though, because all I got to do is multiply 2.654 by the number of atoms that are in 1 mole. So I can do 2.654 moles times 602 hexillion atoms. Now, this is kind of a pain because I got all these zeros, so I'm going to rewrite this using the shortened version of this in scientific notation. Let me just move this up, and instead I'm going to multiply this by 6.02 times 10 to the 23rd, which is usually the version of 602 hexillion that we want to use when we're doing math. When I do this, I can just plug it into a calculator. I'm going to get 1.60 times 10 to the 24th carbon atoms. Oh, I forgot the R. Carbon atoms. There we go. And now, again, sometimes when you see things in scientific notation, it can be a little bit scary, a little bit tricky. So let's put this out of scientific notation. And this is the number of carbon atoms that we have when we put all those zeros in. A whole bunch. 1 heptrillion, 600 hexillion carbon atoms. So that is how we can use moles to figure out the number of atoms we have in something. We can figure out how many moles we have by weighing it, and then once we know how many moles we have, all we've got to do is multiply that by the number of things that are in a mole, and we get our final answer.
Okay. Now, you now know what the molar mass is, okay? The unit of molar mass is grams per mole. Okay? And it's always going to be grams per 1 mole because it is the mass of 1 mole. Molar mass is the mass of 1 mole of that substance, or of 6.02 times 10 to the 23 particles of that substance. So we've learned a bunch of different conversion factors. We have particle ratios. We have 6.02 times 10 to the 23. And we now have molar mass. Okay? So we're going to practice using all of those in separate areas. So I'm going to have you work on page 9. Let's see. Page 9, number 1, A and B. Page 10, number 2, A and B. Maybe not. Okay. And let me just find this page 35, 36. Now, additionally, you guys are going to have a mini test on Thursday on the hydrate lab and the chromatography lab. Now, the hydrate lab, there's not going to be any of the math stuff because we haven't finished the math stuff. Yeah? So it's just going to be the qualitative parts, okay? Because you know what a hydrate is, at least you should have some sort of idea. Tell your partner, what is a hydrate? I don't hear many people telling their partner what a hydrate is. It's a thing. What is this? It's an ionic crystal lattice with water where? Embedded in the structure. And what's holding the water in there? IMFs, intermolecular forces. What happens when you heat this? Do you remember how you got steam coming off your hydrate? Okay, so that is the dehydration process. What do we call this now? The one that has no waters. Starts with an A.
Anhydrous.
This is our anhydrous salt. So, in addition to this, I'm also going to give you a couple of handouts. One is about the chromatography lab, one is a review of the chromatography, and one is a review of the qualitative aspects of the hydrate lab. Tomorrow, I think we will have enough knowledge to be able to start doing the actual math on the hydrate lab, but that will not be on your quiz quest part of test, smallish test that you're having on Thursday. So I will give those two handouts to you as well. Thursday, I'm going to call it a quest on chromatography.
Wait, when do we get the atom? Like today?
Today. And qualitative hydrates, which means no numbers yet, other than like dot 6H2O, because you guys know what that means at this point. Yes? Okay. Let us get you the chromatography one first. Okay. 1, 2, 3, 4. Yeah. No. Okay, no. Let's get you the hydrate one also. Yeah, help yourself. Oh, and is there anyone who has not yet gotten a yellow mole summary? Tomorrow? Yep, yep. Yep, yep, because if you look, that's not quite a mole, is it? Right? It's not, it's like 1,000 times or 1,000 times less than mole, right? So yeah, you can always check that your answers make sense that way. You can say, how much of a mole do I actually have? Oh, that's smaller than that's such a negative. A negative, yeah, exactly. So I would think probably most of you will be able to do all of that and the chromatography and hydrates review tonight. Is that unreasonable? I don't think there's a lot of homework. Yeah, so do these ones. One, two, three, four. Chromatography review. Yeah. Hydrate review. Go. Make sure you come in wolf and then it's much. You know what I mean? It's just a review for the. No, you don't have to have it. We are doing hydrate labs tomorrow. We'll have to. Okay, but yeah, we sort of have to cover, we just want to make more acids and we'll just have to earth, right? And so finding that still in our hydrate lab. We will do that. Good. Yes.
No. Yes.
Okay.